All right, so let's start today then with a question of review from what we talked about on Monday. So the first law of thermodynamics tells us that the change of energy is equal to the heat of the system plus the work of the system. We know that delta E, the change in internal energy, is a state function. We talked about that. What are Q and W? Give you about 10 more seconds and then we'll start talking about it. All right, the key idea here is the idea of a state function. Can anybody tell me what a state function is? Go ahead, Isaac.
Where the outcome is known by how it gets there, or is it the opposite where it doesn't matter?
Okay, it's one of the two. Okay, so what Isaac's referring to here is something called path dependence or path independence. Which one is featured in a state function? It's not the dependent one, it's the independent one. Remember, I gave you the example of climbing a mountain. The change in elevation is a state function. I start here, I end here. Doesn't matter if I go up directly or indirectly, the change in elevation is the same either way. Delta E is a state function. It's not a matter of dependence, but rather independence. So the question is, do heat and work abide by those same kinds of principles? Is my calculation of heat dependent upon the process that is going on? Absolutely. This reaction will generate this amount of heat. That reaction will generate a different amount of heat. Even if I'm looking at the same system, having 5 grams of reactant versus 50 grams of reactant are going to have different results. Heat is path dependent. Work is the same way. One work pathway generates a large amount of PV work. Another pathway produces less PV work. So the correct answer here is this last one. Neither of them are actually state functions, because heat and work both depend upon the process that is taking place. And if you think about it again from our mountain climber kind of idea, the amount of work generated by crawling up the side of the mountain is going to be way different than the amount of work generated by going around the mountain on the trail. The total difference in energy is the same. The way that you got there, very, very different. So if you got that one wrong, don't beat yourself too much about it. There's a reason why we reviewed it. Those concepts, the idea overall of a state function can be a really difficult thing to kind of wrap your head around. When is something path dependent versus independent? We're going to move into our next zone though. So section 3 of your book here is a really long section. We're actually going to spend the next 3 sessions on section 3 because enthalpy is kind of the fundamental overall concept of application when it comes to thermochemistry. We spent 2 days kind of laying the groundwork, but enthalpy is really that central concept that we're going to explore. And the reason we explore enthalpy is because we talked about one kind of way to measure energy on Monday, bomb calorimetry. I put my reaction inside of this vessel. The vessel cannot change in volume, and as a result of that, I can measure the internal energy because since delta V is 0, then everything is just based upon the heat change. And that works for some situations. But here's the problem. Most reactions aren't going to behave that way. Not to mention, a bomb calorimeter can be kind of prohibitive. What if I don't want to look at a reaction that is a combustion reaction? What if I don't want to do a reaction in conditions where the volume is held constant? What if I want to do things at a constant pressure instead of a constant volume? All those questions require that we take a different look at reactions and evaluating their energy. So chemists developed the concept of enthalpy, enthalpy being given by H, where we can measure the heat associated with a process at constant pressure. And with our definition of enthalpy, keeping this at constant pressure basically helps us to negate that P delta V term and focus just on the value of Q. So our definition of change in enthalpy is directly related to the amount of heat that is transferred if we are at constant pressure. Now, why is that good news for us? Well, it opens up the wide variety of possible experiments that we can do. I don't need to have an isolated system like a bomb calorimeter to figure out chemical reactions and the heat transfer involved. Now I can do them in open systems. I can do them in closed systems. I just need to make sure that I account for whatever heat losses might be associated with those processes. But in an open system, and even in most closed systems, that pressure is usually held constant. And the reason we can say it's held constant is because we do most of those kinds of conditions, those experiments, at room temperature, at atmospheric conditions. And atmospheric conditions are easy to acquire. We literally have to do nothing to make them happen. You are being held at a constant pressure right now. The pressure of the atmosphere, whatever it is for today, usually somewhere around 750 millimeters of mercury. That's it. That's all I have to do. And so long as my reaction system doesn't generate so much gas or contract so heavily that I'm unable to actually keep that constant pressure, I'm okay. So I can do reactions in an open system or even in a closed system if I know that I'm going to maintain a constant pressure. And that opens up a wide variety of experiments that we can do compared to bomb calorimetry. Now, in lab, you're going to see the other kind of calorimetry, the calorimetry of constant pressure, known more commonly as coffee cup calorimetry, even though we won't actually be using coffee cups in our lab. It's called coffee cup calorimetry because that is one way that you can do it. Problem with coffee cups usually is that the styrofoam's kind of thin and you get a lot of heat loss to the outside. All that we're doing is we're replacing the coffee cups with a stronger styrofoam container, but it's still going to be constant pressure. And there will be some heat loss. We can't call it a completely isolated system, but it's going to do a much better job of keeping most of that heat inside of the container. So the lab that you're doing this afternoon or tomorrow, and the lab that you're doing at the beginning of next week, all of those are coffee cup calorimeter labs. And so you'll see it in action today or tomorrow. We'll talk more about kind of the calculations associated with it on Friday. And so you'll kind of have a complete picture over these next 4 or 5 days as we're putting these together both in practice and in theory here. Enthalpy introduces a couple of terms that we have seen before, but have not necessarily fully contextualized. You've heard of reactions being called endothermic or exothermic. You might even know some inkling about, what those reactions look like or feel like. Exothermic reactions feel hot, endothermic reactions feel cold. Well, with enthalpy, we now have a full context for what that actually means. In an endothermic process, we are seeing a reaction where heat is entering the system to help the reactants turn into products. As a result of this, delta H, our change in enthalpy, is positive, has a positive sign in it, because the products have a greater enthalpy, a greater amount of heat energy than the reactants did. Easy way to remember that is that enthalpy, enter, and endo are starting with the same sounds. So when heat enters the system, that system is endothermic. Heat enters, it's endothermic. When the opposite is true, so here I have a combustion reaction. Combustion reactions feel hot. Why do they feel hot? Well, the products have less heat energy than the reactants did, and that extra energy gets released to the surroundings as heat. Since we're not part of the system, we're part of the surroundings, we feel that heat as warmth. If heat exits, it's exothermic. The net change here that we're looking at, delta H, is going to be negative. And we can see that because our reactants were at a higher energy than our products. Now, of these two, exothermic reactions are a little bit more common than endothermic reactions. It's much more common to have a reaction release energy than it is to have it absorb energy. All right, any questions so far? All right, let's get into some other properties related to enthalpy then. First of all, enthalpy is what we would call an extensive property. What does that mean? It means that it varies as the amount of substance varies. So some common extensive properties are things like mass, volume. If I have a larger object, it's going to take up more space. It's going to have more mass as a result. Enthalpy is the same way. If I burn 5 grams of a substance versus 50 grams of a substance, the 50 grams of substance are going to generate more heat because there's more of it. Now, because enthalpy is an extensive property, there are a couple of consequences of that that are actually advantageous to us. First of all, we can think of enthalpy values when it comes to chemical reactions as being part of our stoichiometry scheme. And so what I mean by that is, let's take a look at this reaction that we were given. The combustion of hydrogen in oxygen to make water vapor. Well, from a stoichiometry standpoint, this is saying that 2 moles of hydrogen will result in 483.6 kilojoules of energy being released. 1 mole of oxygen will release 483.6 kilojoules of energy, and 2 moles of water are related to that same 483.6 kilojoules of energy. Basically, we can run stoichiometric conversions directly off of the balanced chemical equation and the given value of our stoichiometry, of our enthalpy rather. So that's one consequence. I've said several times in this class already that the whole point of stoichiometry is to tie different concepts together through moles. This is one more thing that we can tie together through moles, because this links up the relationship between energy and the moles of our substances in the chemical reaction. Now, additional consequences, things that will come into play more so on Friday than today, but are some things that we want to kind of log in the back of our minds. Because of this extensive nature, because of the link in stoichiometry, we can manipulate our delta H values by manipulating our equations. So, for example, if I flip around my reaction, so the top reaction has hydrogen and oxygen reacting to make water. If I flip that around and do the decomposition of water to create hydrogen and oxygen, those two enthalpies are identical. The only difference is the sign, which way the energy is going. In the top reaction, we see that it's negative. It's going out of the system. That's an exothermic process. which we would expect for a combustion reaction. The bottom equation, we see that that sign, the enthalpy, is positive. Energy is going into the system, which again makes sense for a decomposition reaction. Decomposition reactions usually require energy input to break the bonds of the substance so that it'll decompose. But if I wanted to manipulate this furthermore, let's say that I cut this bottom reaction in half. So it's just water vapor making hydrogen and 1/2 of an oxygen. Well, the delta H value for that would be exactly half of the one on top of it. So 483.6 divided by 2, 241.8. And it would still be positive because the reaction above it was positive. All I did was cut it in half. Now, when we talk about Hess's law, this kind of manipulation is going to become a lot more common and a lot more useful. But right now, I just want you to kind of understand that this relationship exists in the first place. So one other manipulation, one other area that we want to consider is this one. When it comes to chemical equations, where we start to look at energy, you'll see that phases are going to be part of those equations pretty much universally. And the reason why is because the phase of matter is actually going to make a difference in terms of the amount of energy that is required or released. So take, for example, this small change. Top line, I've got the combustion of hydrogen and oxygen to make water vapor. Water in the gas phase. Exothermic reaction releases 483.6 kilojoules. If I were to change the way that this equation functions by having it form liquid water instead of gaseous water, notice what it does to my enthalpy. The enthalpy is not the same. It's almost 90 kilojoules less. Exothermic. Why is that? Because there is a phase dependence. Different energy outputs, different energy requirements are going to be there for liquids versus gases versus solids. And we already kind of knew that, but we had to be explicit about it now. We know that gases have more energy than liquids. We know that liquids have more energy than solids. We just have to make sure that we recognize that as we're trying to quantify the energy that is involved in the process. So we're going to talk about two different types of calculations today. The first kind of calculation is this one. This is called a heating curve. And what a heating curve shows is it shows two different things at the same time. It shows us the temperature that a particular substance is compared to the amount of energy that has been put into that substance. And this is called a heating curve because we're seeing the result of heating this substance and the energy of that substance increasing. If we were to draw this particular diagram in reverse, starting at a high temperature and going to a low temperature, we would call that a cooling curve instead of a heating curve. The energy would be released instead of input. But if we look at what we're exploring here, we're going to notice that there are several different points of emphasis here. So the first one here, we've got ice at negative 30 degrees Celsius. Our second bullet, we have ice at the freezing point, 0 degrees Celsius. This third box, we have water at 0 degrees Celsius. Moving up, we can see that our temperature has now changed. We have water at 100 degrees Celsius. Moving on, we have steam at 100 degrees Celsius. And then finally, we have steam at 130 degrees Celsius. So in total, our amount of water hasn't changed, but we see 6 unique applications of water in this particular curve. Either with one phase changing temperatures, or with one phase changing into another phase. Now the question becomes, how do I go about, if I were trying to calculate this amount of energy associated with any one of these transitions, how would I go about doing that? And what I have to recognize is that there are 2 different kinds of energy transfers taking place here. There are energy transfers that are taking place at so I have temperature changing transfers of energy. So I've got ice changing from 30 to negative 30 to 0. I've got water changing from 0 to 100. I've got steam changing from 100 to 130. All of these would be considered temperature changing heat transfers. And then further, I have a different kind of transformation that's taking place. If I look at these 2 transitions that are marked here with pink, notice that those 2 transformations, temperature didn't change in those. Those are phase changing heat transfers. So when it comes to heating and cooling curves, I have 2 different types of calculations that I can do. One of those types involves processes where the temperature is changing. I'm warming up a substance in the liquid phase. I'm cooling down a substance in the gas phase. whatever it is. The phase isn't changing, but the temperature is. The other kind of change is where I see an isothermal constant temperature phase change. And so, as you might expect, there are two different types of calculations associated with these different types of transfer. So for the first kind, where I've got my temperature changing transfers, I'm going to end up using the heat equation that we talked about with the first law of thermodynamics. Q is equal to mc delta T. What is important for us to remember that specific heat value, that value of C, is dependent on the phase of the substance. Now, those specific heat values, those you would pull out of a table of values. They would be given to you in some kind of way. But in each case, you would take the mass of the substance, multiply it by its specific heat at whatever phase you are, and then determine the change in temperature. And change in temperature is always final temperature minus initial temperature. So that's the temperature changing transfer. Again, we've seen this at least to some degree. Maybe haven't done a calculation with it yet, but we've seen this to some degree when we were talking about the first law of thermodynamics, about the overall definition of heat. Now, what about the second type of transfer? The one where we have a phase change. Since delta T in a phase change is 0, we can't use Q is equal to mc delta T. What we have to do instead is we have to use a different equation. Here's our different equation. Q is equal to N times delta H. N is the number of moles of substance. Delta H is a constant value that depends on the phase change. And there are two types of phase changes here. We have the delta H FUS. This is called the heat of fusion. And this is for phase changes that occur between the solid phase and the liquid phase. Delta H VAP is something known as the heat of vaporization. And this concerns phase changes between the liquid phase and the gas phase. And notice, we're giving you 4 different equations here. But the only difference in any of these equations is just on what value of delta H do I use and the sign convention. Is heat going into the system because it's an endothermic process, or is heat coming out of the system because it's an exothermic process? So is the substance gaining energy and going to a more scattered kind of phase, liquid to gas, solid to liquid? Or is it losing energy and going to a more condensed phase, gas to liquid, liquid to solid? That's the only difference in any of these four equations. What value do I use? Is it positive or negative? The real meat of the sandwich here is this top equation, this generic one. Q is equal to N times delta H. If we can remember that, we can pretty much apply it to any scenario where there's a phase change. Now, like I said, these phase changes, these heat values, these are values that you would be given. So each substance has a heat of fusion and a heat of vaporization associated with it. Water's a little bit funny. It has multiple heats of vaporization, and that's primarily because water is a liquid for such a wide range of temperatures that we have to factor in some of its evaporation effects. Whereas for most other substances on this list, the temperature difference between freezing point and boiling point isn't nearly as big of a range of temperatures. And so we generally think of them as just having a singular value instead of multiple values. All right, let's look at an example problem. So let's say that we were given a scenario where we had to calculate how much heat is it going to take to convert this amount of snow into water that is about to boil. And if we think about it from a heating curve kind of standpoint, so going back, we're basically covering these first four states, these first three conversion steps. We need to heat up the snow, we need to melt the snow, we need to heat up the water to the boiling point, but it doesn't say that we're actually boiling it yet, we're just getting it to that temperature, so we don't need to do any of step 4. With calculations like these, we need to break them down stepwise, keeping in mind one really important idea, that the total heat is going to be the sum of all of these individual heats put together. So if I'm trying to figure out how much total energy is getting put into this snow, I need to figure out how much heat is in each of the steps and then put the 3 steps together. Okay, so first step, I'm heating up the snow from -18 to 0 degrees. Got a temperature change here. I'm going to use Q is equal to MC delta T. So my mass value, 275 grams. The C value, the specific heat for ice, had to look this up earlier today. It is 2.09 joules per gram degrees Celsius. Again, that's something that you would pull out of a textbook, out of a reference table, not something that you're going to have to know or memorize. Delta T, remember we're going from final to initial, so 0.0 minus -18.0 degrees Celsius. 0 minus -18 is +18 degrees Celsius. So multiply those 3 numbers together, 275 times 2.09 times 18 to three significant figures. I get 10,300 joules or 10.3 kilojoules. So that's the first step. We would do that kind of step for any kind of heat transfer. In fact, we could do step 3 right now. Same basic idea, 275 grams of water. The specific heat of water in the liquid phase is 4.184 joules per gram degree Celsius. Temperature change, I am ending at 100 and starting at 0. So total change there is 100.0 degrees Celsius. So 275 times 4.184 times 100 to three significant figures is 115,000 joules or 115 kilojoules. So notice in calculation 1 and calculation 3, the setup is basically the same. The only difference is, since I have a different phase, I'm going to have a different specific heat value. And I just need to make sure that I have the correct values for the final temperatures and the initial temperatures to calculate delta T properly. For the one in the middle, phase changes are isothermal, same temperature. So I can't use the same equation. I've got to use a different one. And the one I use is this one. Q is equal to N times the delta H of fusion. Well, to use this equation, I need N. I need the number of moles of water. So I've got to do that conversion first. 275 grams of water. There are 18.02 grams of water in 1 mole. So 275 divided by 18.02 gives you 15.3 moles. And then Q is equal to the 15.3 moles multiplied by the molar heat of fusion. Where do I get that value? Gotta get it off of the table. So the molar heat of fusion is 6.01 kilojoules per mole. So that's what I'll use. (15.3) times 6.01 is 91 point, oops, excuse me, round that correctly, 92.0 kilojoules. So now I have my three values. I've got 10.3, 92.0, and 115. Keeping in mind my rules for significant figures here, I'm adding these three numbers together. So decimal place matters. This one has 1 decimal place. This one has 1 decimal place. This one has 0 decimal places. So we're going to round to the one with 0 decimal places. (10.3) plus 92.0 plus 115 rounded to the ones place, we get 217 kilojoules. And that's a positive 217 because, again, heat is going into that system. So any questions about heat curve calculations? These problems can be kind of involved. Luckily, on that assignment, there aren't too many of them, just enough to kind of get you familiar with doing those calculations. Now, there is one kind of calculation that we didn't quite get to, but it's related to something I talked about before. And it's the using the molar relationship to calculate energy from a stoichiometry standpoint. So we'll talk about that a little bit on Friday. I think you'll probably be able to kind of figure it out on your own for the homework assignment, though, because it does fit very nicely just into what we've already seen and discussed. But if you have any questions about it, feel free to reach out to me, let me know. On your way out today, go ahead and hit up the stoplight question so you get that participation point for today. And I'll see you on Friday to talk about calorimetry and Hess's law. Have a good afternoon.